Good morning, my dear friends. Welcome to Bishnupriya's chemistry blog. Today we will discuss about measurement of uncertainty, types of uncertainty, type A uncertainty, type B uncertainty, about precision, about repeatability, about reproducibility, and why is measurement of uncertainty is needed in laboratory as per ISO 17025 2017. So without delay, let's start the topic. First, we have to discuss what is measurement of uncertainty. The measurement of uncertainty is the degree of doubt and its significance in the result of a measurement, and it is calculated by combining and expanding various factors that contribute to uncertainty in the measurement. So without delay, let's start today's topic about measurement of uncertainty. Now first we have to discuss what is measurement of uncertainty. The measurement of uncertainty, it is a parameter associated with the result of a measurement, and that characteristics the dispersion of the value that could reasonably be attributed to the then come to expressing uncertainty of measurement. How you express uncertainty measurement? For example, if we say that the length of a certain rod measures 20 centimeter plus or minus 1 centimeter at the 95% of confidence level, then the result could be written as 20 centimeter plus minus 1 centimeter at a level of confidence of 95%. Now what it says? Now this statement says that we are 95% sure that the rod is between 19 centimeter and 21 centimeters long. So it says that we are 95% sure that the rod is between 19 centimeter and 21 centimeter. Then what should be measured and calculated and what not be? Then come to its concept and what mistakes we made. And the mistakes made by the operators are not measurement of uncertainty, and it should not be counted as contributing to uncertainty, and that should be avoided by working carefully while working in a laboratory. And tolerance are not also uncertainty. They are acceptance limit which are chosen for a process of a product. And what are the specifications? Specifications are not also uncertainty. A specification tells you what you can expect from a product. And what is accuracy? Accuracy or rather than inaccuracy is also not the same as uncertainty. Unfortunately, usage of this word is often confused. Correctly speaking, accuracy is a qualitative term. Example, I could say that a measurement was accurate or non-accurate. Then why should we need uncertainty calculation? What is this requirement? As per ISO 17025 2017. Now as per clause 7.6 and measurement of uncertainty as per ISO 17025 2017, clause number 7.6.1 says that laboratories shall identify the contribution to measurement of uncertainty when evaluating measurement of uncertainty all the contributions that are significant, including those arising from the sampling, and shall be taken into account using appropriate method of analysis. And clause number 7.6.2 says that a laboratory performing calibration including of its own equipment shall evaluate the measurement of uncertainty for all calibration. For this we have to refer enable document 141. Also we can refer ISO IEC guide 98 and ISO 21748 and the ISO 5725. Then what is the subclause 7.6.3 says? Now it says a laboratory performing testing shall evaluate the measurement of uncertainty where test method preludes rigorous evaluation of measurement of uncertainty, and an estimation shall be made based on an understanding of the theoretical principle of practical experience of the performance. Then come to what is uncertainty. Now every measurement has an uncertainty associated with it unless it is an exact and counted integer such as the number of trials performed. And every calculated result also has uncertainty. It is related to the uncertainty in the measured data used to calculate it. This uncertainty should be reported either as an explicit plus minus values as an implicit uncertainty by using the appropriate number of significant figure. And the numerical value of plus minus uncertainty values tells the range of the result. For example, a result reported as 1.2.3 plus minus 0.05 means that the experiment has some degrees of confidence that a true value falls in between 1.18 and 1.28. And what is uncertainty of measurement? Now, it is a parameter associated with the result of a measurement that characterizes the dispersion of the true values which could reasonably be attributed to the measurement. And uncertainty is always with us and errors also be corrected. And it is a vital in interpreting results of deciding if they are fit for the purpose. Then how can we quantify uncertainty? For this, we have to check precision and accuracy. The relationship of accuracy and precision may be illustrated by the familiar example of firing a rifle at a target where the black dots below represents on that target. And the good precision does not necessarily imply good accuracy. However, if an instrument is well calibrated, the precision or reproducibility of the result is also good to measure its accuracy. So here the pictorial representation of precision and accuracy. Then come to errors and type of errors. Now the errors is an abbreviation is the difference between the observation and the actual true value of the quantity observed. And returning to our target analogy, error is how far always a given a shot in the form of bullseye. Since the true value or bullseye position is not generally known, the exact error is also unknowable. And comes to types of error. Errors are often classified into two types. One is systematic error and second one is random error. And what is systematic error? A systematic error may be caused by fundamental flaws in either the equipment or the observer or the user of the equipment. For example, a balance may always read 0.001 gram to light because it was zeroed incorrectly. In a similar vein, an experimenter may consciously overshoot the endpoint of a titration because he is wearing tinted glasses and can't see that fast color of the changes of the ending. Then come to errors. What is random error? Now, random error arises from unpredictable variation. For example, uncontrolled environmental condition. Then inherent instability of the measuring equipment and the personal judgment of the operator or observer. Then come to systematic errors. Now, what is systematic error? That is reported in calibration certificate of instrument and of reference standard, purity and COA values. What is COA? The certificate of analysis value, and this can be isolated and minimized. Quantification of both are also possible. Here is the pictorial representation of accuracy, precision and bias. The measurement value which is at fixed time. So we have to calculate mean value, standard value and the method of bias. So there are two types of error. First come to random. It is the inherent in all process. It is unpredictable. It reduce must change the process and is vary in a completely and non-reproducible way from measurement to measurement, and it can be treated statistically. And in non-random, it is due to special or assignable causes. It is predictable. It is simpler to eliminate. It is frequently difficult to discover and can result in high precision but poor. The related terms and phrases in MU calculation. That is, accepted reference value is a value that serves as an agreed upon reference for comparison. And the accuracy of measurement, the related terms and phrases in MU calculation. Now first come to accepted reference value. It is a value that serves as an agreed upon reference for comparison. The accuracy of measurement. and it is the closeness of agreement between a test result and accepted reference value. Then come to arithmetic mean. This is the sum of values divided by the number of values. And then come to measurand, a quantity subject to measurement of analytic. Then come to repeatability. It is the test result are obtained by same method and identical test items in the same lab by same operator by same equipment within short interval of time. Then come to reproducibility. What is that? This is the test result are obtained within the same method and identical test item in different lab by different operator using different equipment. Now, repeatability, it is the closeness of the agreement between the result of successive measurement of the same measurement carried out under the same condition of the measurement. Now, it is the test result are obtained by the same method and identical test item in the same lab by same operator by same equipment within short interval of. In reproducibility, it is the closeness of agreement between the result of measurement of the same measurement carried out under changed condition of measurement and the test result are obtained within the same method and identical test item in different lab by different operator using different equipment. Then come to ISO guide approach on MU calculation. That is specify the measurement including complete equation. It is quantify the significant uncertainty in all parameters and from statistics of repeated experiment and by any other means its theory, certificate and judgment, and it expressed as standard deviation. It combines according to standard principles. Now, what is standard uncertainty? Now, uncertainty of the result of a measurement expressed as standard deviation. Then come to type A uncertainty. Now, what is type A uncertainty? Now, for the calculation of MU measurement, there are two types of uncertainty involved. First one is type 1, second one is type B. First come to what is type A uncertainty. It means that uncertainty evaluated by the statistical analysis of series of observation. And in type B uncertainty is evaluated by means of other than statistical analysis of series of observation. Here is the histogram diagram of measurement of uncertainty. Type A uncertainty. First come to standard uncertainty. Then we have to calculate type A uncertainty from the repeated result. For analysis, we have to repeat the test. From that repeated result, uniform distribution or normal distribution, also standard uncertainty. And from type B uncertainty, from certificate and literature, rectangular division and triangular division, and coverage factor 95%. Types of probability of distribution associated with the variable. What are the variable involved in for measuring the measurement of uncertainty? First come to normal distribution, and it is used when an estimate is made from repeated observation of a randomly varying process, and uncertainty is then given in forms of standard deviation. And what is standard deviation of the mean is x by x means. And the relative standard is the deviation RST or coefficient of variation percent, and uncertainty of a variable with given 95% or other confidence interval is given as mu x is k by 2 for 90% probability or k by 3 of 99.7% probability. Then come to types of probability distribution associated with variables. Rectangular distribution is used when the information is taken from a certificate or specification which gives associated uncertainty without specifying the level of confidence. For example, if the concentration of calibration standard is quoted in certificate is 1000 plus minus 2 mg per liter, for example, if the purity of cadmium is quoted as 99.99 plus minus 0.1%. And in these cases of uniform rectangular distribution, here is the distribution as such that individual units or purity or probability are more likely to be near extreme. Therefore, an estimate is made by applying rectangular distribution. Hence, assumed standard uncertainty is half of the width or square root of 3. Then come to types of probability distribution associated with variables. Then come to triangular distribution is used when distribution is such that occurrence of mean value from range is most probable. Therefore, an estimate is made by applying triangular distribution. For example, if a manufacturer quoted volume of volumetric flakes of 100 ml as 100 plus minus 0.12 tolerance of 0.1 ml, in this case, nominal value is most probable. Therefore, an estimate is made by applying triangular distribution. Hence, assumed standard uncertainty is half width divided by square root of 6. Then come to combined uncertainty. Now, it is the component of uncertainties are all combined to produce an overall uncertainty. Now, it is the sum of all uncertainties may cancel each other out. Some may be interdependent. And type A and type B uncertainty factors, when combining all factors, it need to be converted into smaller units of measuring: percentage, gram, ml, degree centigrade, and unit less. And you use the root over of UA2 plus UB2. This is the pictorial representation of combining uncertainty. The standard deviation and established error propagating theory. Then come to expanded uncertainty. And in some cases, the combined standard uncertainty needs to be multiplied by the appropriate coverage factor. This is called expanded uncertainty, where mu is the k plus UC, where k is the normal 1.96 or 2 for 95% confidential level also. Then the personal bias in reading analogs instrument also affects measurement of uncertainty, and the uncertainty of weights and volumetric of equipment, and the instrument resolution or discrimination also affects, and the value assigned to the measurement of standard and reference material also affects, and the value of constant and other parameter obtained from external source and used in the data reduction algorithm, and an approximation and assumption incorporated in the measurement method and procedure also affects. The variation in repeated of observation of the measurement under apparently identical conditions. Then come to source of uncertainty in recovery estimation. Now this is the repeatability of the recovery experiment, uncertainty in reference material value, and the uncertainty in added spike quantity, and the poor representation of native analyte by the added spike, and the period and restricted mass between experiment and the matrix, and the effect of analyte or spike level and recovery, and the perfect match of spike or reference material analyte level and analyte level in sample. Then come to uncertainty component. Here is the contribution to the uncertainty. RST. Here is the graphical representation of uncertainty component. Then come to method of stating test result. When reporting the test result and its uncertainty, the use of excessive number of digits should be avoided. Unless otherwise specified, the test result should be reported together with expanded uncertainty at 95% level of confidence in the following manner. For example, measured value is 100 plus 1 units, uncertainty measurement is plus minus 0.1 units. Then come to step-by-step process of mu calculation. First, let us take an example. Define the analyte which is being calculated with the formula for calculation. Look all the probable causes of mu such as repeat, reproduce, analysis data from type A and data from other sources involved in type B. This is the main vital point. So, create a fishbone diagram to understand the probable source and the subsource for mu. First, generate data on both type A and type B. So, here is the fishbone diagram. First, what is the component needed? Now, standard CRM, volumetric flags, stock purity, volume text, pipette, uncertainty of pesticide, weighing balance, standard calibration, precision, and sample preparation. Then come to type A calculation. So, perform the repeat and reproducible analysis and parameter being evaluated. So, we have to name and S1, S2, S3, S4 for the repeat test of the sample, and the calculate the average above as per formula. Then calculate the standard deviation as per formula. Then calculate standard uncertainty. Then calculate relative standard uncertainty as per formula. It is called as also relative type A uncertainty. Then come to type B, calculation of type B uncertainty. For example, electronic balance. For calibration certificate or external energy, we get the values of specific range at 95% level, which is 1.996 units. From balance query says the value what we observe and we will get from our certificate says 8.1.2%, which is supplier manual, and the errors we have to find out. And assuming rectangular distribution and putting formula, we have to find out its expanded uncertainty, standard uncertainty and relative uncertainty by putting all the formula. Then after weighing balance, then come to pipette. Says suppose it is 10 ml. From calibration certificate or report of analysis, we will get our 95% follows process for balance and uncertainty due to tolerance and repeatability says 0.1. So by putting formula, we have to also calculate all the standard deviation and expanded uncertainty by putting the formula for pipette. Then come to type B uncertainty as per the preparation of standard. For factors which is balance and uncertainty, volumetric flux and uncertainty due to purity of standard may also temperature also affects. For balance uncertainty, we have calculated the uncertainty by U balance by the square root of all the deviation which we found. Then for flux, we have to also calculate. For standard purity uncertainty from the certificate value, the COA value, certificate analysis value, will also get the 99.5% 5% of uncertainty, and we have to also calculate its standard uncertainty. And examples of sample preparation and recovery. What are the factors used? Balance uncertainty, volumetric flux uncertainty, uncertainty due to the repeated recovery data, and maybe temperature also. And the balance uncertainty, U balance is the square root of all the component, and for the flux square root of all the component, and from the recovery studies for validation data, and which will come from the repeat of analysis for recovery details 10 determination says at 50 ppm. So we have to calculate the average value. Let us say it 48.5 ppm, and its standard deviation we have found by calculation is 0.5 ppm. So standard uncertainty 0.5 by square root of 10, and its relative standard uncertainty is 0.5 by square root of 10 into 0.5, and its standard uncertainty also by putting formula we have to calculate standard recovery. So CU is the means combined uncertainty is the square root of all types of A uncertainty plus all types of B type of uncertainty. And then come to expanded uncertainty. And expanded uncertainty is the combined uncertainty into factors of 2 for 95% confidential level, which you will get from our calibration certificates provided by the external supplier. And these all are units less. And expanded uncertainty with unit is expanded uncertainty into average. So result is average plus or minus expanded uncertainty in units. So this is all about uncertainty. Then come to calculate uncertainty in an Excel sheet. Let's take an Excel sheet. Let's take the parameter chloride. For the calculation of uncertainty, we have to use our Excel sheet. First, we have to write the heading calculation of uncertainty measurement. Then we have to write which type of water is, whether it is drinking water, wastewater, surface water or groundwater, we have to mention. Then we have to write our sample wide and the date of testing and the parameter which we calculate their uncertainty. Here I have calculated uncertainty for chloride parameter. Then first come to type A uncertainty. So here I have taken 5 source component, 5 repeatability test. Then by putting formula, so we have to calculate its mean value. Then by putting formula, we calculate the standard deviation value. Then come to standard uncertainty and relative uncertainty. Then come to type B error, coverage factor. So we will get it from our certificate. Then due to balance weight required for testing. So in type B we have to calculate the repeatability test. Then type B, so we have to calculate the measurement of uncertainty due to balance, then due to pipette. And what are the equipments used for the measurement of chloride parameter? Here I have taken balance, weighing balance, pipette, volumetry, flask, burette. Okay, then so from this we have to calculate the standard deviation by putting formula and the standard uncertainty and relative uncertainty. Then we have to calculate their combined uncertainty and expanded uncertainty. Combined uncertainty by calculating all standard deviation, standard uncertainty, relative uncertainty. Finally we have to calculate combined uncertainty, then expanded uncertainty. Then come to our results. Is 47.8. So for chloride mean value is 47.2, 47.8.2, and expanded uncertainty is 0.035. So our measurement of uncertainty result reporting is will be like this: 47.82 plus or minus 0.03584. Okay. So if you like my video, please like, share and subscribe. Thank you. Bye bye. Thank you for watching.